Hello, we'll be doing chapter number 16, Reactions in Aqueous Media. And this is a continuation of chapter number 15. And in 15, we did chemical equilibrium. And so now we are going to apply the same equilibrium content into reactions of acids and bases. And with that brief introduction, I'm going to share my screen with you. Share my screen with you, and so you can see the content for the introduction for acids and bases and the chemical equilibrium. First is I'm going to give a quick review so that you have an idea of what we are talking about. And then I will do another slide in which I will show you how to calculate the equilibrium constant for acids or bases, since you already have an idea how to do that. So here, in the introduction part, we are going to describe what types of acids are there and their characteristics, differentiate between the types of acids, write the equilibrium constant for the ionization of water, write expressions for dissociation of weak acids and bases, determine the relation between the equilibrium constant for a weak acid, equilibrium constant for the conjugate base of the acid, and water itself. So there are three definitions that are currently used to define acids and, of course, bases, because they go hand in hand. The first definition is the Arrhenius definition, which states that any substance, when dissolved in water, produces an H plus ion in solution, then that substance is considered as an acid. At the same time, an Arrhenius base is a substance that, when dissolved in water, produces OH minus ions. The OH minus ions are called as the hydroxide ions. And the reaction of an acid and base will produce salt and water, and therefore the reaction is stated to be a neutralization reaction. Now, the deficiency of this a simple definition of an acid and base is this, that H plus ion, which is produced in water, is basically a proton. So as per Arrhenius definition, a proton can exist freely. However, this is not true. And also, Arrhenius acid definition does not explain reactions in other media. So existence of free proton cannot explain the reactions in other media, but the advantage is that it is the simplest definition of an acid currently available. The second definition, the second type of acid is the Lowry-Bronsted acid. Now, this is one step higher and encompasses all the acids that were defined under the Arrhenius acid or base, and therefore Lowry-Bronsted definition of an acid or base is as follows. A Lowry-Bronsted acid is considered as a proton donor, and a Lowry-Bronsted base is considered as a proton acceptor. Remembering that unless there is a proton acceptor, a material cannot behave as an acid. Therefore, in such reactions, you will see that you must have two reactants on the left-hand side and two products will be formed on the right-hand side. And as an example, just in a couple of slides, we will see that. And the last definition, which encompasses both the Lowry-Bronsted acid definition, the Arrhenius definition, is the Lewis acid definition put forward by G.N. Lewis. And G.N. Lewis describes an acid as an electron pair acceptor and a Lewis base as an electron pair donor. When we come to this last part, you will see how we can define the hydrated cations of various elements that are there, or the hydrated forms of anions, how they are explained based on the Lewis acid definition. Why? It also explains why the oxyacids behave as oxyacids, why those compounds that have lower oxidation number and higher oxidation number tend to have different type of structure and geometry, and therefore they are able to behave as acids. Now, beyond that, this is a simple definition that Arrhenius put forward. So anything that produces hydrogen ions in water is an acid. Anything that produces hydroxide ion in water is a base. On the other hand, now, the Lowry-Bronsted theory explains, so it expands on the Arrhenius theory, and it is a good theory. And it says an acid is a proton donor, a base is a proton acceptor. Now, when we want to explain proton donors, remember, proton donors can be molecular compounds, cation anions, or hydrated metal cations. So you have different types of reactions over here showing you how you can get a proton donor. So look at the left-hand side. You have HNO3, nitric acid, is dissolved in water, and it gives the nitrate ion, NO3 minus, plus the hydronium ion, H3O plus. Now, as soon as you look at this equation, you see two important concepts straight away there. That if you look at the formula of the HNO3 ion, that is, all elements are the same. HNO3 and the nitrate ion, NO3 minus. The only difference between HNO3 and NO3 is one proton. Let's look at water. Now, water on the left-hand side has got H2O, but when it accepts a proton, it becomes H3O plus, and H3O plus is an acid, and H2O on the left-hand side was a base. Therefore, we see, or we come to one very important conclusion, that when we define Lowry-Bronsted acid-base, there are two acid-base pairs, and these are called as conjugate pairs. And the conjugate pairs in the first expression is HNO3, which is an acid, NO3 minus is a base. And the base and acid differ by one proton H. Same thing, when you look at H2O and H3O plus, H3O plus has one more hydrogen than H2O plus, and therefore H3O plus is the acid and H2O is the base. And these conjugate pairs help us understand how the reaction goes. Now look at, it says, so HNO3 is a molecular compound. Now let us look at ammonium, a cation. The ammonium ion, NH4, can donate a proton to H2O, which then becomes H3O plus, the acid part, and NH3 is the base. And so again, you have the conjugate acid base, NH4NH3. So NH4 has more hydrogen atoms than NH3, and therefore it is the acid, and the base component is NH3. And in the case of water, same, H3O has more hydrogen than H2O, and so H3O is the acid and H2O is the base. Now, the anion part is, look at the bicarbonate ion, HCO3 minus plus H2O. Now, HCO3 minus will donate a proton to H2O, thereby getting itself converted to the carbonate ion CO3 2-, and then again you get the H3O+. And I hope that you are following the trend and see how the whole system works. So now, in the case of HCO3 and CO2, CO3 2-, you find HCO3 is the acid, CO3 2- is the base, its conjugate base. And then look at the metal, hydrated metal cation, FeH2O hexahydrate. So Fe hexahydrate, water molecules, 3+. So if it is there, it is dissolved in water, then you get FeH2O 5OH. So it is iron pentahydrate or penta-aqua hydroxyl 2+ ion that is there. And so now, because the one of the water molecules opened or donated a proton to H3O+, whatever remains behind is the OH- ion, and therefore you see how the reaction goes down. Now, the proton acceptors can be, again, either molecular compounds and or anions, and you see NH3 plus H2O gives you NH4 plus OH-. Production of an OH- ion indicates that the solution would be basic. CO3 2- plus H2O gives you HCO3 minus AQOH-. Now, look again at the conjugate acid and base pair. Water donated a proton to the carbonate ion to form HCO3. So HCO3 and CO3 2- is the acid and base pair, differs by 1 H, and H2O and OH- are the acid and base conjugate pair, again differing by 1 proton. Now you see in these two reactions that you can have water can donate or accept a proton, and such molecules we call them as amphiprotic. So now, using the Bronsted definition, we have NH3 as a base because it accepts a proton, and the water itself is a proton donor. Now, Lewis acids and bases is a more general concept. Lewis acid is a substance that can accept a pair of electrons from another atom to form a new bond. Lewis base is a substance that can donate a pair of electrons to another atom to form a new bond. And the example of this is shown over here. The formation of the hydronium ion, H3O+, is an example of a Lewis acid-base reaction. The proton, H+, can accept a pair of electrons donated by the water molecule to form the H3O+ ion. And this is a Lewis acid. And now you can practice some of these examples with your concept evaluation. Make sure you do it so that there is no excuse saying, I don't know how to do it, because they are really simple and it's very easy to follow. Next, I want to introduce, when we look at Arrhenius definition, Laurie Bronsted definition, and the Lewis definition, most important of all is the water molecule, H2O. Now we know that water is a neutral compound, but in actual fact, water has ions also included in that neutral molecules present, but the amount of H+ or H3O+ ion and OH- ion is very, very small. And so when we write an equilibrium constant expression for water, please note that H2O, it is just like how you normally write an equilibrium constant, Kw is equal to H3O plus concentration times OH minus concentration divided by the reactant concentration H2O raised to 2. I've not been able to include that, so it is to the power 2. But the amount of water present is in such a large extent that we can literally eliminate its presence or its change in concentration because it hardly changes. And therefore, we can write Kw as equal to H3O plus times OH minus. Remembering that for every H3O plus formed, there is a 1 OH minus produced at the same time. This means that the concentration of H3O plus and OH minus in water are equal. There is no question of almost. They are equal in neutral water. And the value of Kw at 25 degrees Celsius, 20 degrees or 25 degrees Celsius is 1 times 10 raised to minus 14. From this particular expression, you can see that the concentration, the square root of Kw will give you the answer 1 times 10 raised to minus 7, because negative 14 divided by 2, a square root, means you take out the square root of it, 1 by 2, the answer is 10 raised to minus 7. Now, 10 raised to minus 7 means that 1, the concentration of H3O plus is equal to OH minus, and in 10 million liters of water, you have 1 ion of H3O plus and OH minus. And therefore, the statement that the ionization of water is extremely small, and so the change in the concentration of water can be neglected. And when we write or calculate the equilibrium constant for any acid or base. And before we go further to define an acid or base, I want to do a brief, quick, fast introduction to the pH scale. pH stands for the negative logarithm of the hydrogen ion to the base 10. The base 10. Now, for neutral solutions, we know that the concentration of hydrogen ions is 10 raised to minus 7, and the OH concentration is also minus 7. So if you take out the pH for neutral water, hydrogen ion will be 7, because negative logarithm to the base 10 of a concentration of 10 raised to minus 7 is actually minus 7 times minus 1, which is equal to 7. So we can find out whether a solution, just water, can be used to express whether a solution is acidic or basic. Because for an acidic solution, the pH will be less than 7. And for a basic solution, the pH must be greater than 7. Because at neutral point, the pH is equal to 7. Furthermore, we can see that hydrogen ion pH 7 plus POH 7 is equal to 14. And if you take out the negative logarithm of Kw, which is negative logarithm to the base 10 of 10 raised to minus 14, then you get pKw is equal to 14. And this is a very important concept that you have to remember in order to do all calculations, because we know that from the expression pH plus POH is equal to 14, if you know either pH or POH, you can find out not only the concentration of the pH value, but also the concentration of the ions that is present. Why do we need to know this? Because we are working across a very large concentration range. And when you work around a large concentration range, you want small integers to explain those numbers. So, in brief, right now, then, just before we go to the last couple of slides, here is what it is. Water and the pH scale. In neutral solution, water, the hydronium ion concentration equals the hydroxide ion concentration. Both are equal to 1.00 times 10 raised to minus 7 moles per liter. In an acidic solution, the hydrogen ion concentration, that is the hydronium ion concentration, is greater than the hydroxide ion concentration. And therefore, H3 plus must be greater than 1.0 times 10 raised to minus 7. And OH will be less than 1.0 times 10 raised to minus 11. And in a basic solution, it is the reverse. Now, this is a slide that repeats everything beforehand, and let's go now. How do we write? So, how do we write the dissociation constant of an acid? And this is a brief because there are the remaining units, sub-slides will go through all this, but I do not want you to forget what you studied in chapter 15. The strength of a weak acid can be expressed with the equilibrium constant Ka, where A stands, the subscript A stands for the acid. So HA is a generalized form of a monoprotic acid. If it has to behave like an acid, it must be able to donate a proton to water, forming H3O plus and A minus ion. Then the strength of the weak acid is related to its equilibrium constant Ka, which is the ratio of the product H3O plus times the concentration of the A minus, the conjugate base divided by the acid. That is the first one. And at the bottom, in the top equation, water has been eliminated because it says that it is very, very small. But at the bottom, I have written the water, included the water molecule, so that you will see, understand the whole equation, that generally K is equal to reactants divided by the concentration of the product. So better keep it in that format. Now, if B is considered as a weak base, then exactly the same equation will be there. The reactant, the base B, will pick up a proton from water and become BH plus an acid, and OH minus the base that is there. And the equilibrium constant Kb will be BH times OH minus divided by B, the concentration of the base, and H2O is in large quantity. But if we keep the H2O, then I want you to see what is the relation between Ka, Kb, and Kw. Now here, the Kb is the conjugate base of the acid, weak acid. And therefore, when we look at that, you see that the equilibrium constant for the acid we saw is written as H3O plus A minus divided by HA times H2O concentration. And for the conjugate base, at the same manner, we can write A minus plus H2O gives you HA plus O minus. Therefore, the conjugate base, the equilibrium constant for the conjugate base will be OH minus times HA divided by A minus times H2O, where H2O is water, A is the conjugate base concentration, OH is the hydroxide ion formed during the particular reaction, and the amount of acid that was produced, even though it is very little. Now, look at what happens when we multiply the conjugate, the Ka of an acid, by the Kb of the conjugate acid. That is, you multiply the equilibrium constant for the acid and its conjugate base. And when you do that, you get a large, big expression in which, if you remove the common terms, A minus, HA, and HA, you get the expression OH minus concentration times H3O plus concentration divided by H2O times H2O. As the concentration of water does not change as shown before, it follows that the product of the equilibrium constant for a weak acid and the conjugate base of the same acid is always equal to Kw, called as the autoionization constant for water. And with that, I'm going to stop sharing.